Hi and welcome to this Leaving Cert Higher Level Maths video where we're looking at calculus and specifically integration as area. So in this video we're going to look at definite integrals, we're going to look at calculating area using integration, we're going to look at the trapezoidal rule for estimation of area and also average value of a function. Now, if you have not already revised the basics of integration, I'd advise you do that. I've linked the video in the description below. So let's talk about what a definite integral is. So a definite integral is one where we're going to get a value as our answer. It looks quite similar to our indefinite integrals, but it has what we call limits of integration. So these small numbers that appear at the top and bottom of the integral sign, so that's stretched out S. So what we're going to be doing is we're going to be evaluating, so finding a value of the integration with substitution. So we're going to integrate it first, then we're going to sub in the values, and what we're doing is getting an answer, a number answer, as opposed to working backwards from differentiation and getting a function. So the main differences between definite and indefinite integrals are the first, that we have limits, the second, that we're going to get a value answer, but the third is that we are not going to include that constant of integration, that plus c, because when we do the substitution piece, if the plus c was there, it would eventually just cancel itself out. So if you want to add it in the first few times and see that it disappears and it's not needed, that's absolutely perfect. So example 1, let's evaluate this integral here. So we're going to use our log tables, page 26, which are our rules of integration. And step 1 is to actually integrate. So 3x squared. So add 1 to your power, divide by your power, and we're going to evaluate this between 0 and 2. We can simplify this, so it makes it a little bit easier to work with. So we're actually working with x cubed, which we're evaluating between 0 and 2. How we actually do that evaluation is we sub in the upper limit, so in this case 2, so we have 2 to the power of 3, and then we take away when we sub in the lower limit, so in this case 0 to the power of 3, and that gives us 2 to the power of 3 is 8, minus 0 to the power of 3 is 0, so my final answer for this is 8. So let's look at one that has multiple terms. So just like when we are differentiating, when we integrate multiple pieces, we integrate each piece individually. So again, you can see that this is a definite integral. It asks us to evaluate, so our answer is going to be a number, and it also gives us those limits of integration, so 2 and 4. So let's integrate first. X squared, add 1 to your power, divide by your power. Add 1 to your power, divide by your power, and when we have 3, we're adding 1 to our power. Remember, that is an x to the power of 0, so this becomes 3x. Again, remember, no need to put in that plus c, because when we do our substitution, they will cancel each other out. We're going to evaluate this between 2 and 4. So the first step is to put this in with the upper limit. So you sub in the upper limit first. So that is going to be 4 cubed over 3 minus 4 squared over 2 plus 3 times 4 minus, and then you sub in the lower limit. So it's always the bigger minus the smaller. So 2 cubed over 3 minus 2 squared over 2 plus 3 times 2. And we can go to our calculator. So we'll go to our calculators, and the first bracket, when we put that in, we get 76 over 3 minus, and then our second bracket, and really watch your signs here. So there's a minus, and then whatever we get in our second bracket, we get 20 over 3. So that simplifies to 56 over 3. I would leave it as a top-heavy fraction unless they tell you otherwise, but if you want to, it's 18 2/3 or 18.67. So let's look at an example where we have to do a little bit of work on the actual expression before we integrate it. So we have 1 over the square root of x. Now, our rule for polynomials, so x to a power, is add 1 to our power, divide by our power. Now that means that all of our x's have to be written in the form x to a power. So the first thing we're going to do is we're going to take our 1 over root x, and we're going to change it using our rules of indices. So square root is to the power of a half. And then if it's underneath the line, we can bring it above the line and it makes it a negative. So 1 over the square root of x is actually x to the power of minus a half. Now, although that doesn't look as nice, that is a much better way for us to work with integration. Well, it's the only way we can work with integration, but also with differentiation. So we're going to integrate, it's definite integrals, so between 4 and 9, and we're going to integrate x to the power of minus a half with respect to x. So that is what we're doing the rule to. So for example, dx means you do the rule to the x's. So let's integrate. We add 1 to our power. Just be very careful with your fractions here and negatives. So you're adding 1 to your power, minus a half plus 1, we get plus a half. And then you divide it by your power, which is dividing by a half. Now, dividing by a half is the same as multiplying by 2. So that actually simplifies down to 2x to the power of a half. And we're evaluating that between 9 and 4. So step 1 is we sub in the upper limit. So this is 2 times 9 to the power of a half. If you prefer, you can put that back as a square root. You don't have to, but you can. And you could do a little bit quicker in your head. So we end up with 2 times 9 to the power of a half. And that's your first answer. Take away 2 times 4 to the power of a half, which is your second answer. So 9 to the power of a half, square root of 9, that's 3. 2 times 3, that's 6. Minus 4 to the power of a half, square root of 4, which is 2. 2 times 2, which is 4. But your calculator can do all this work. And our final answer here is 2. So let's look at rules where we're dealing with not just polynomials, not just x to powers, but where we're dealing with some of our other things that we see on page 26. So in this case, we have e to a power. Now, when we learn to differentiate e to the power of x, we realize that actually e to the power of x does not change. We have 2 little rules here for e to the power of x. We have e to the power of just x, and that stays exactly the same for integration and then also for differentiation. And if we had e to the power of something x, so for example 3x, we would end up having to multiply it if we were differentiating, or dividing if we're integrating. So that's 1 over a, the derivative of the power. So in this case, we're not too worried because we just have an e to the power of x. So that e to the power of x is not changing. The coefficient, that number 4 in front of it, often students get confused, like, well, what do I do with the 4? If we were dealing with that as an x to a power, that 4 would just sit there. And it's going to do the same thing here. It's just going to sit there and not get involved. So step 1, we integrate. 4 doesn't get involved. E to the power of x stays e to the power of x. And that's it. So it will be exactly the same. So we're going to do some substitution. So we have 4e to the power of 5 minus 4e to the power of 2. Because we're dealing with e's, these are going to give us not particularly nice answers. They're going to give us decimal. So let's put that into our calculator and see what we get. So into our calculators, 4e to the power of 5 minus 4e to the power of 2. We get 564.096. Now in a question in an exam, they'd be very clear about how many decimal places, etc. So biggest takeaway here is be careful not to apply that rule of add 1 to your power, divide by your power to everything. That rule is specifically for x to a power. So now let's look at 9 to the power of x. So we go to our log tables, page 26, and we look for a rule. And here is our little rule there. It says when I have a number, a constant, a to the power of x, I integrate that as a to the power of x divided by the natural log of a. So for us, it looks like 9 to the power of x does not change. And then ln's the natural log of a, which is 9. Again, be careful not to assume this is add 1 to your power, divide by your power. That only works when it's x to a power. Here we have a number to the power of x, which is different. So we come along and we do our substitution. We have 9 squared divided by the natural log of 9. So our first one, minus. Now, sometimes we can get a bit, I suppose, lazy and think that, oh, sure, when I sub in 0, I get 0. That's not going to happen all the time, especially when we have x as a power. Because when we have something to the power of 0, it's going to give us 1. So here what we end up with is 81 divided by the natural log of 9 minus 9 to the power of 0 is 1 over the natural log of 9. And that has to go into our calculators, and let's see what we get. So 36 point, let's go 2 decimal places here, 36.41. So just remember your rules are there. Anytime you're doing integration, have this page 26 open in front of you. Even if you think you know your rules off by heart, it's always good just to double check and make sure you don't do anything silly. Because sometimes the rules there are enough to remind us that actually 9 to the power of x is not add 1 to the power divide by my power. So let's look at some integration with trigonometric functions. Now, the trigonometric functions, because we can see them kind of, they could be paper 1 as a function, paper 2 as trigonometric or trigonometry in general. We can see calculus appear, and especially some integration. And we're going to explore a bit more about what kind of things it could be asked with regards to integration. So it's an important one to have and to be able to work with. Also to mention here, when we're integrating, integration has to be quite simple. We can really, at this point, all that's left on our course is to integrate individual terms. If there is any kind of multiplication there, so when I mean multiplication, I don't mean like 4 in front of it. I mean if there's a function in front of it, like an x in front of it, or for example, cos by a sine. We have no rules to deal with that. So instead, what we'd have to use is work with our identities of sine, cos and tan, and work with page 13, 14 and 15 in our log tables. Now I'm not going to go deeply into it here, but I have a separate video that looks at specifically calculus for trigonometric functions, and I've linked that in the video below, in the description below, if you would like to go through it in more detail. So let's talk about cos of 2x. So we go to page 26 and cos integrates to sine. Now, when we have our log tables, it says cos to sine, but I actually have a cos of 2x. So that 2, we have to deal with it. And this is like a backward step of the chain rule and probably the most complicated thing that we have to do in integration. And it's going to be the sine of 2x, but we end up having to divide our answer by 2 because of that 2 in front of the angle x. So if we think of this as its own piece, so cos of 2x, that is cos of the angle 2x. It integrates to the sine of 2x because it's not as simple as what we see in the log tables as just x's. We need to adjust it by dividing by what is effectively the derivative of 2x, so the derivative of 2. It really looks like we just pull the 2 down and divide by it. When we work in differentiation, we ended up multiplying by that number there. And like I said, if you want to explore this in more detail, just click the link in the video. Click the link for the video in the description below. So this is our integral, and we're going to evaluate this between pi over 4 and pi over 2. So they are both in radians. So pi, that's kind of our hint that the angle is in radians. They will not tell you when we're working in integration that these are in radians. This is something you need to know. I'll talk about that in a second, about the radians, why we use it and so on. But for the moment, just if you want to use your calculator, make sure your calculator is in radian mode. And you might say, well, what other option do I have? And we do have page 13 if you so choose to use it. So into your calculator, but like I said, if you're going to use your calculator, change it to radian mode now. So here we get a 0 minus, and this works out as a half, so we get negative a half here. If you want to work, like I said, page 13, that's absolutely perfect as well. We get sine of pi all over 2 minus sine of pi over 2 all over 2, and you should get exactly the same answer. So let's talk very briefly about why we always use radians in calculus. So again, I cover this in the video on trigonometric functions and calculus in general, but just to very quickly kind of confirm that when we're working in definite integrals, the angle will always be given in radians. And again, we can tell that it's radians because of that pi. Now just be careful, because I often say to students, when you see pi, think radians, but that's only when we're talking about angles, because pi also exists in formulas for our cone, for our sphere, just for area and circumference of a circle. So I suppose don't get confused and see pi and go, oh, I have to change my calculator to radians. That only works if you're working with an angle, so think sine, cos, and tan. So just very quickly think about what we mean by radians. So you would have worked with radians in trigonometry, so hopefully you've already covered trigonometry, and there is a video that goes back over all trigonometry, including radians in more detail. But what a radian is, it's when we measure a turn where the length of the arc is equal to the radius. So you can see my little diagram here on the right. So we have a radius r, but this one radian creates a turn that has an arc equal to the radius. So all circles will have 2 pi radians. So 2 pi is 360 degrees. And you can kind of make a link here to our length of our circumference, so 2 pi r. So that idea that the length of the outside of the circle is 2 pi r. So 2 pi times the radius, because there are 2 pi radians and each radian draws an arc r. So we can kind of see, okay, suddenly this makes sense. So radians, when you first meet them, might feel a bit like, oh, what? Degrees make so much more sense, but actually degrees are quite arbitrary. Somebody has divided a circle into 360 degrees, and that kind of happened because they thought there was 360 degrees or 360 days in a year. We now know that's a little bit not as accurate. 360 is also a lovely number. It has lots of factors. So, but it is quite a random number. Like if we were to do that now, we might divide it into 100 pieces. So actually, when we're working with the radians, make more sense. Again, you might not agree with it right now, but I promise you they do. So what radians do, it helps us to relate linear measure to angle measure, and that is quite important. But from a kind of calculus point of view, well, like, why can't I use degrees? That's it. So why are they not using degrees? Why are we being forced in calculus to use radians? So the first one is like, well, if we were thinking of this as plotting graphs, radians make so much more sense. So if we were to plot this with the x-axis and y-axis having the same number of jumps, so as in 1 unit on the x-axis is equal to 1 unit on the y-axis, then degrees actually, we wouldn't see anything happening. So let me show you. So this is a degree function. It is sine of x. It is plotted over 360 degrees. And because sine has a min and max at 1 and -1, you can barely see anything. And the reason for that is because what I've done is I've set my x and y axis to having the same jumps. So you can see that one box means 20, because otherwise I wouldn't be able to fit this on the screen. But because we use that, you know, the same scale on the x and y axis, we're not seeing much of a change, which makes it very hard to work with. Now, let's compare this to a radian graph where we have one box is 1, and suddenly we can really see our sine graph. So this is the same graph. The only difference is my x-axis is currently showing as radians. So if we think of a circle having 2 pi degrees, so 2 pi radians, which is 360 degrees, that means a rotation, a normal rotation is 2 pi degrees. Pi is 3.14, so 2 times 3.14, we're just talking just over 6. So you can see in this graph, just after 6, I have that function has done its full rotation. So it's much easier to see what's going on. We get a much better sense of it. So that's kind of, you know, reasoning number 1. Radians make more sense when we're graphing it on the same scale. The second thing, I suppose, is because our rules of differentiating and integrating, they're coming specifically from a function that uses radians. And you might think, does that make a difference? And it actually really, really does. So for example, this is where it comes from. And I think very simply back to differentiation from first principles and things like that. But we can basically figure out that the limit as x goes to 0 of sine of x divided by x, that gives us 1. But this only works if x in radians. So we don't need to go into the complicated kind of thinking around it. But I suppose to understand that when you look in your log tables and you're given the rule for differentiation and for integration, those rules have come about. Remember, they're shortcuts, but they've come about from functions that are using radians, not degrees. So it's really, really important that anytime you are using sine, cos, or tan, or any trigonometric functions versions of those, when you're working in calculus, you must use radians. So if nothing else from these two slides, if all you can take away is that you must always use radians, that's enough. So let's talk about integration as a purpose. So when we first learn differentiation, it's kind of like, well, what's the point of differentiation? The point is it gives us slope. So it's a rate of change. It's how something is changing. When you first when you're first introduced to integration, generally how it's introduced is, well, it's kind of the backwards of differentiation, which is exactly, yes, what it is. But it also has its own purpose. And the purpose of integration is actually to calculate area. Now, the reason we might introduce this a little bit later than, day one of differentiation, you're like, differentiation is slope. The reason we introduce this a little bit earlier is because or a little bit later, is because if we want to calculate area, we need definite integrals. So obviously definite integrals come after learning about integration as the backward step for differentiation. So it's just to try make the best sense of it. But integration, the purpose of it is to calculate area. So if somebody says, what does integration do? And it is area. So if I want to get the area underneath a function, or really between a function and the x-axis, I would integrate the function with respect to x. So between the function and the x-axis with respect to x, between two values. So here's what we'd look like. So here's a function. If I want to find that shaded area in blue, I would integrate between a and b, where a and b will become those limits of integration that we have in our definite integral. So this is really, really good because we have quite, I suppose, an irregular shape here. We could kind of do some approximations and we'll explore that later in the video. But at the moment, this integration gives us a very accurate answer for area. And the reason for that is it's breaking it down into smaller and smaller pieces until we take this function as the continuous line that it is. So we can integrate with respect to x or with respect to y. So here is what would happen if I integrated with respect to y, so dy. That means that I'd be looking at the area between the curve and the y-axis. So it works both ways. So you can work with respect to the x-axis, so that's between the curve and the x-axis, or with respect to the y-axis, so between the curve and the y-axis. So suddenly that dx dy, that piece at the end, that is telling us a little bit more than just what we do the rule to. We're understanding, well, what will that do in terms of a practical question with area? So let's look at an example. We're being asked to find the shaded area below. So here we're being asked to set up the definite integral. Once we've set up the definite integral, we're kind of back to what we were doing in the first 6 examples. So let's get the area by integrating between 3 and 5. The function 1 over x squared with respect to x, because I'm going down to meet the x-axis. So before I do anything, I suppose I want to rewrite 1 over x squared as x to the power of minus 2, because then I'm better able to integrate that. So I have 5 and 3, and then I have x to the power of minus 2 with respect to x. So my area is going to be add 1 to my power, so I get minus 1, and that's going to be between 3 and 5. And I divide by my power, so my minus 1. So I'm going to have a minus, a minus x to the power of minus 1. Again, if you want to do some tidy up there, you can. So x to the power of minus 1 is 1 over x. If you prefer that for substitution, that's fine. We're going to sub in the upper limit first. So that's minus 5 to the power of minus 1. So that's our first piece. And then we subtract. And again, here we're going to have to be really, really careful with our signs. So that minus comes between it. And we have a minus in the bracket. 3 to the power minus 1. My suggestion when you're doing any of these is for the moment kind of work out each bracket separately. It's good to kind of see where you went wrong. It's easier to check your work. Yes, in a lot of cases you go straight and get the answer, but just to be careful. The calculator piece can actually be quite tough, making sure you've typed it in correctly, making sure you've all your signs, putting the brackets in the right place. So practice it by getting each bracket separately, at least to start, and then getting your final answer. So the first bracket is minus 1 over 5. minus, and then this is minus 1 over 3. So that actually a minus minus gives us a plus. And we can add them in our calculators and we get 2 over 15, and that is square units. So there are no units like centimeters, etc. on our graph. So this area would be in square units. So where each unit on our x and y axis would be squared. So let's talk about the idea of positive and negative area. So this has been dealt with. If you've done coordinate geometry, we would have worked out the area of a triangle. And if you can remember back to that formula, the area of the triangle formula when we work in coordinate geometry, it has absolute value signs, which means we always take it as positive. Because when we're working in a coordinate grid, like we are here with functions, often we can get answers that are negative that don't actually make sense as negative. So for example, if you are looking at the distance between 2 points, you might get the answer as negative, but obviously distance can never be negative. Same with area. Because we're dealing with kind of positive and negative numbers, often we can get like a negative area, but there is no such thing as negative area. So the first thing is to understand, well, where does that negative area exist? Well, if we are integrating with respect to x, so if we're integrating against the x-axis, above the x-axis is positive, below the x-axis is negative, which kind of makes sense to us because that's kind of what we would have always thought of. Think back to your inequalities in algebra and so on. Above the axis is positive, below the axis is negative. So if we have a scenario where we are taking pieces of area from above and below the x-axis, we have to be a little bit clever. So let's look at this example here. We have 3 sections of our graph. Now you might think, can I just go straight from -1 to 4? And you can't, because this little piece of area will be negative, this will be positive, and this will be negative. So if I go and do that whole thing straight away, the positive and negatives will actually kind of cancel each other out a little bit. So we need to make sure that we work out each area piece individually, ensure it's positive, and then add them together. So this can make that question a little bit longer than we might expect. So let's work out what the area would be. So we have area of the first piece. So I'm going to call this piece 1. And like we said, that's negative. I'm going to call that piece 2. And I'm going to call this piece 3. So the area of the first piece, we're going to integrate it between -1 and 0. We're integrating 3x minus x squared. And that's with respect to x. Let's work that through. So add 1 to your power, 3x squared, divide by your power, add 1 to your power, divide by your power, and we're going to figure this, we're going to evaluate that between -1 and 0. So when we do that, we get 3 times, sorry, we're subbing in 0 in first, because that's actually bigger, over 2 minus 0 cubed over 3 minus 3 times, watch your brackets here with your negative, -1 squared minus -1 cubed over 3, and that first bracket gives us a 0, and let's go to our calculator for the second bracket. So yeah, 0 minus, and that's 11 over 6, so the first area is -11 over 6, but it can't be negative, so we force that to be a positive 11 over 6. So that's what we mean by ensuring that we work with, I suppose, each piece individually, and to make sure that when we work out each piece, we take it as positive. So that's my answer for A1. Let's work out the next part, so we'll do the same thing for A2. Now A2 will end up being positive, so we're integrating that between 0 and 3, and we have 3x minus x squared dx. You've already done the integration, so you don't have to kind of even think about this. If you're comfortable with having done it and you're happy with your answer, we know that this is what it works out as. This time we are subbing in 0 and 3, so my first substitution is going to be 3 times 3 squared all over 2 minus 3 times cubed all over 3, and then we take away, when we sub in 0, 3 times 0 squared over 2 minus 0 cubed over 3. When we work that out, I know my second answer is going to be 0. Let's go to our calculator for the first. And we get 9 over 2. So that's our final answer for A2, which is 9 over 2. And the last piece we want is our A3 piece, and then we'll add them together. So our third area is going to be, A3 is going to be integrating between 3 and 4. 3x minus x squared dx. So this is going to be 3x squared divided by 2 minus x cubed over 3, and we're going to evaluate that between 3 and 4. So that is 3 times 4 squared over 2 minus 4 cubed over 3, and then we're going to take away in that second bracket 3 times 3 squared over 2 minus 3 cubed over 3. Now, we've actually already worked out that second bracket because that was 9 over 2 in our last question. So you really only need, or the last area, so you just need to go to your calculator for that first bracket. We get 8 over 3. So 8 over 3 minus 9 over 2. And we get negative 11 over 6. But again, we know that the area cannot be negative, so we force that to be a positive 11 over 6. So we have our three pieces of area here. So we have 11 over 6. So actually the area of 1 and 3, they were identical. Could we assume that they're identical? We just need to be a bit careful, and we need to work with the idea of the quadratics being symmetrical. But yes, you could if you were very confident about that, but don't assume just because they look like it. So my total area is going to be 11 over 6 plus 9 over 2 plus 11 over 6, and that will give me my total area. Now, as I said at the start, if we were going to try and do that integration in one piece, we would be in trouble because the areas for the first and the third section will come out as negative, and they would end up being subtracted rather than added. So the area, 9 over 6, 9 over 2 plus 11 over 6. And that gives us a final answer of 49 over 6 square units. So quite a long question, not hugely difficult, but there's quite a lot in it. Obviously, the more steps you have to do, the more likely it is that there's going to be a small error or so on. So just to be careful working through any questions like this, and not to power through and try do it in one step, to be very mindful of that idea of positive and negative areas. If we want to get the area with respect to y, so against the y-axis, we're also going to have this positive and negative issue. So the positive part, when we work against the y-axis, is to the right, and the negative part is to the left. So think of it in terms of, that makes sense because the positive numbers are to the right of the y-axis and the negative numbers are to the left of the y-axis. Let's look at an example here where we are actually working with respect to y. So here I have x and I want to integrate it. Now I'm going to integrate not this whole thing. I have to work this out because we have no kind of special rules for multiplication. So we want to work this through. So let's split our bracket and multiply that out. So we get y squared minus y minus 2y plus 2. So that's y squared minus 3y plus 2. So I'm going to integrate this and that's the squared with respect to y. So dy, which means against the y-axis. Now, if I want area, I need my limits, which I usually read from my graph. But as you can see, there are no limits here. So how do we do that? Well, these are on the y-axis, which means the x value is going to be 0. So we can go a step further and kind of say, well, let's figure out what the y values are when this is x equals 0, so when y minus 2, y minus 1, where that equals 0. This is just factorization, so we let each factor equal 0, because if I have two things that multiply to give me 0, one of them has to be 0. So either y is 2 or y is 1. So on my graph, there is y equals 1 and y equals 2, and they become my limits of integration. So we have a little bit of work to do from our graph. So again, nothing terribly difficult, but just a little bit of thinking required. So let's integrate. So add 1 to my power, divide by my power, add 1 to my power, divide by my power, and here we have 2y. We're integrating between 1 and 2, so this is my area. So we sub in 2 first, so 2 cubed divided by 3 minus 3 squared over 2 plus 2 times 2, that gives me my first bracket, minus, we do exactly the same thing, but we're subbing in a 1 cubed over 3, minus 3 times 1 squared over 2, plus 2 times 1. If we can see it there on the side of the page, and then we go to our calculator. That first bracket gives us 2 over 3 minus the second bracket, which gives us 5 over 6, and we get minus a sixth when we do that. And again, area cannot be negative, it's just where we're looking. If you think about what we just said, to the left of the y-axis is where we get negative, so our area is actually 1 over 6 square units, so we take it as positive. So it doesn't matter what our answer is, whether it's positive or negative, we always take the area as being positive. We understand that the reason we're getting this as negative is because it's to the left of the y-axis. So the next step will be to look at how to get the area between two curves. So we're going to work with the idea of the area we just worked with and extend it slightly. So the first thing you're going to have to do to find the area between two curves is find the x values where the curves meet, and this is going to give us a and b. So if we take our example here, we have two functions, f of x and g of x. They meet at the points where x is a and x is b. So we're kind of getting the points of intersection, but we don't really care about the y. Now in some exam questions, they'll specifically ask you for the points of intersection, and if they do, we will get the points of intersection. But if not, we're fine with just having those x values. The second step then is to work out the area under the upper function and subtract the area under the lower function. So what's happening here, and I'm going to try and sketch it out. So here's our upper function, this one here, and we want the area underneath it, which will give us this shape here, which is fine, but it's not what we want. So what we then do is we come along and we take away this piece underneath the lower function. So this piece that I've kind of gone over in red, and that should leave us with the piece in between. So the upper function is always the one that's higher in this section, and the lower function is the one that's lower. So what we're going to have is the area is going to be integrate the upper function, so f of x, between a and b, then take away the integration of g of x between a and b. Now that will work all the time. However, if your two functions are both polynomials, for example, so they can be simplified, my advice would be simplify them first. So if you can, rather than doing two sets of integration and then substitution, which is tedious as we've seen, why not simplify it so you only have to do that once? So for example, the area can be the integration between a and b of f of x minus g of x dx. So we can actually do that simplifying before the integration piece. That's my preferred method. I think if you can do it, it's going to be simpler, it's going to save us time, it's going to save us space, and just generally less prone to error. So let's take an example here. I have a linear function and a negative quadratic, and I want to find the area between them. So step one is to find the x values at a and b, so where they meet. So let's take our two functions. I have x plus y minus 1 equals 0. Excuse me, that's my linear. We then have y equals minus x squared minus x plus 2. This is my nonlinear. Go back to your algebra of how to find points of intersection between linear and nonlinear functions. We isolate and sub in. So my suggestion would be, let's take that linear. So I'm going to label these 1 and 2. So I'm going to take my linear and I'm going to isolate my y. So y equals 1 minus x. And then what I'm going to do is I'm going to let 1 equal to 2, because now I have 1 y equals and 2 y equals. So by that logic, I will have 1 minus x from my equation 1 is equal to minus x squared minus x plus 2 of my second equation. So I like this method. You could that could be substitution as well. It works pretty much the exact same. But really what we want to do is we want to get rid of that y, because we don't care about it. We want our x. You want to leave your x in there. Now let's work this through. So we get x squared. I'm bringing everything to the left hand side. You have a minus x plus x that undoes itself. So 0. 1 minus 2. So that's minus 1 equals 0. We actually have a difference of 2 squares here. So let me just get rid of this for a second. So we have an x squared minus 1 equals 0. So you might be like, oh, how do I solve that quadratic? It's actually a much easier one. Don't forget about highest common factor and difference of 2 squares. I have x minus 1, x plus 1 equals 0. If you're going to bring the minus 1 across the equals and square root it, remember that when you add a square root, you need to make sure that you put in both a plus and a minus. So what we have here is, there's my minus 1 and here's my 1. So any integration I'm going to do are between those 2 points. So I'm going to integrate. So to get my area, I'm going to integrate between minus 1 and 1. I'm going to integrate the upper function, which is my negative quadratic. So minus x squared minus x plus 2. Take away the lower function, which is now we need to work with this in terms of y equals. So this is 1 minus x. We've already isolated that. So the reason we want to write it like that is because we don't want to have a y in there. We want to use this form here. So y is equal to 1 minus x. So it's just a rearrangement. Now you can integrate this as is. However, like I said, I prefer to simplify it first. So I'm going to do a little bit of work on this. So I have a minus x squared that stays as is, minus x plus x, and you get a 0, plus 2 minus 1, and that's a plus 1 dx. And that's what we're integrating, which is so much easier than trying to integrate those two pieces together. So my area is going to integrate. So add 1 to my power, divide by my power, and add 1 to my power. So that's just 1x or x. So we're going to evaluate that between minus 1 and 1. So let's give ourselves a bit more space to do that. So we're going to sub in 1 first, and then we're going to take away subbing in a minus 1. Plus 1 minus subbing in. Watch all your signs here, using your brackets when you're doing your substitution. And let's work out each bracket individually. So my first bracket is 2 over 3 minus. My second bracket is minus 2 over 3, but we already have a negative in the middle as well. So you're subtracting a negative 2 over 3, which gives us an area of 2 over 3 plus 2 over 3, which is going to be 4 over 3 square units. So let's see how this question was asked on an exam paper. So this is an exam question from the 2018 paper 1. It is question 6, and it gives us two functions on the graph below. We have k of x, which is a cubic, x to the power of 3, and we have h of x, which is a linear, which is x. Remembering that both of these just mean y, h of x and k of x, what we're basically trying to do is, for part A, find the coordinates of the points of intersection. So we want to find the points of intersection of a function or functions, and the easiest way to do it is to find out where are the two functions equal. So something like this. So that is, where is x equal to x cubed? Now we're going to find 3 points. We have a point here we have a point here, and we have a point here. So I'm going to bring everything to one side. I'm actually going to bring the x across, so that's minus x equals 0. I can use highest common factor, so x is common, leaving with an x squared minus 1 equals 0. I can break down that bracket further as a difference of two squares, so x minus 1, x plus 1 equals 0. And I let each factor equal 0. So either x equals 0, x equals 1, or x equals minus 1. So we can see that that on my graph means that's minus 1, that's my 0, and here is my positive 1. Now, they didn't ask us just for the x values, they asked us for the points of intersection, so we'll need to go back and get our y values. The easiest way to do that is by using h of x equals x. So basically, the function, the y value will be equal to the x value. So my first one is h of 0 equals 0, so the point is 0, 0. H of 1 equals 1, so the point is 1, 1. And for the last one, h of minus 1 equals minus 1, so my point is minus 1, minus 1. So some common errors that can happen here, students often divide across by x rather than pulling it out. It's really important that we never divide across by the variable, because if there's a variable there, it means that we need it. We need to get that third answer, and especially when you look at the graph and see that we are looking for 3 places where they meet. So part BI asks us to find the total area enclosed between the two graphs, or between the graphs of the two functions. So we're looking for two pieces. We're looking for this piece here. And bearing in mind where it is, that part's going to be negative. And we're looking for this piece up here, which is going to be positive. Now, these two areas are definitely equal because we have an x to the power of 3. So it's a cubic, but it is a symmetrical cubic. So we have a line, and that line is obviously going to be symmetrical. So we can work out one of the areas and we can simply double it. So the easiest place to work would be this piece here. So I'm going to call this area 1. We're going to integrate between 0 and 1. We have figured those limits of integration out from part A, where it asked us to find those points of intersection. We're going to do the upper function, which is x, take away the lower function, which is, let me get rid of some of these brackets. So we're going to have x take away the lower function, which is x to the power of cubed. With respect to x, there is no required cleanup there because nothing can be simplified. So let's integrate that. So add 1 to your power, divide by your power, add 1 to your power, divide by your power, and we're going between 0 and 1. So the first one we're going to sub in is 1, so we get 1 squared over 2 minus 1 to the power of 4 over 4. We take away 0 squared over 2 minus 0 to the power of 4 over 4. This works out in our first bracket as a half minus a quarter, so we get a quarter minus 0, which is going to work out as a quarter. Area 2 will be exactly the same. Therefore, the total area is going to be a quarter plus a quarter, which is a half. And remember, that's our square units. So although this is not integration, this is something that on the higher level papers we've often seen included in integration questions, which is why I'm covering it here. So we're going to talk about the area approximation using the trapezoidal rule. So on page 12 of our log tables, which is the area approximation, we have a trapezoidal rule. The trapezoidal rule is basically a way for us to calculate the area of an irregular shape. So you can see the shape at the top there, but it is an approximation, so it's not perfect. When we work with integration, it gets us the exact area. So they like to ask these questions comparing the approximation method, so trapezoidal rule, to the more accurate method of integration. So in our log tables here, we can see that the shape has been broken into not rectangles, but as close as we could get, given the top is an irregular kind of, you can see this kind of curve as opposed to being straight across. We break these into columns which are all of the same width, and that width is h. The y value gives us the height at each point. The more of these we have, the more accurate our answer will be. Depending on the question, there will be different numbers of those y values, which is why the formula is y1, y2, y3, y4, ... yn. So yn will change depending on the question. The formula itself is the A area is approximately, that funny looking equals is approximately equal to h, so the width of each of these bands divided by 2, times y1 plus yn, so the first plus the last, plus 2 times all the other ones in between. So let's have a go at working with this and see if we can make sense of it. So let's look at an example from the 2015 paper 1. This is question 3. We have f of x, which is a negative quadratic, minus x squared plus 12x minus 27. We're being asked, first of all, to complete the table below. So we want to figure out, well, what is f of x, what is y when x is 5, and that works out as 8. And then what is the function when x is 6, and that works out as 9. And then when it's 8 is 5, and where 9 subbed in, we get a 0. So use table 1 in the trapezoidal rule to find the approximate area of the region bounded by the graph of f and the x-axis. So we need to break this up for the trapezoidal rule. So let's label our f of x, which is another way to say y. And we have y1, y2, y3, y4, y5, y6, and y7. Our h, it's the jump between the x's, and these should all be the same. So in our case, h is 1. So the area formula is going to be h over 2 times y1 plus our last y, which in this case is y7, plus 2 times all the y's that we haven't used yet, which is y2 plus y3 plus y4 plus y5 plus y6. And subbing that in, we get the area will approximately be equal to 1 over 2, 0 plus 0 plus 2 times 5 plus 8 plus 9 plus 8 plus 5. That can go into our calculators, and we get 35 square units. So just be careful putting that into your calculator. And that's the use of the trapezoidal rule. So quite straightforward. Generally, we're given a table. Make sure that you're labeling correctly. Make sure you understand the h, so that's the jump. So that's our jump in x-axis. The jumps in the x values along the x-axis, they should be consistent. And then the y values, you can label them in your table. So part B then asks us to find the definite integral of f of x with respect to x between 3 and 9. So basically we are now working to find a more accurate answer for area using the definite integral. So our area is going to be integrating between 3 and 9 our function, which is minus x squared plus 12x minus 27 with respect to x. So that's going to be add 1 to our power, divide by our power, add 1 to our power, divide by our power, add 1 to our power, and we're doing that between 3 and 9. We can actually tidy that up a little bit, so we get minus x cubed over 3, we get plus 6x squared. You don't need to tidy it up, but it just sometimes can be easier when you're putting it into the calculator to have the numbers as simple as possible. So when we do that, we're going to sub in 9 first. So minus 9 cubed over 3 plus 6 times 9 squared minus 27 times 9. That's our first bracket. And then our second bracket is minus 3 times cubed over 3 plus 6 times 3 squared minus 27 times 3. Let's work out each bracket individually and then find our final answer. The first bracket gives us a 0 minus. The second bracket gives us a minus 36, which gives us a final answer of a positive 36 square units. So part B2 on this question asks us to use our answers from the above to find the percentage error in your approximation of the area correct to one decimal place. So let's pull our two answers that we had previously. So in A part 2, we found the area was approximately equal to 35 square units. In B part 1, we found the area was 36 square units exactly. So what is our percentage error? So if we're asked the percentage error, and this could be in any section, what you want to do is you want to put the error over the correct amount and then multiply it by 100 or 100 over 1, whichever you prefer. So our error is going to be, it doesn't matter about positive or negative, because they're not going to think about it, it's, you know, a positive error or a negative error. We're just going to think of it as the error. So the approximation was 1 unit out over the correct answer. This is where it gets tricky, because students are very good at putting the error over something, but it's what's the something. So it's always over the correct. So that's going to be over 36. And you multiply that by 100 or 100 over 1. It's the same thing, just over 100 makes life a little bit easier. So when you go to your calculator and do that, want to change it to a decimal, they want to correct to one decimal place. We get 2.7777, which is 2.8%, which is our percentage error. So let's talk about the average value using integration. So this is a question we see thrown into so many section B questions, even some section A questions, where they just ask us to get average value. So there is a formula for it, but before we get into the formula, let's see if we can get an understanding of what exactly we're doing. So here's a little quick question for you. I have a little diagram there on the right, and the shaded area of this shape is 24 square units. Can you find the height? So hopefully you can. Looking at that shape, we could say, well, I don't know the height, that's what I need to work out, but I can work out the base because it goes from 1 to 5, so the base must be 4. I know my area is 24, so basically 4 times what is 24, and hopefully you can work out that that is 6. Now, what if I added a slightly more challenging question and I said the area of this shape is 24, what is its height? Now, the issue we have here is the height is not constant. So what height am I really asking you for? So if I wanted one height, really what I'd be asking for is an average height. So if I said this to you, let's say, what's the average height? And you say, well, on average, 4 times 6 would be 24. So the average height will be 24, which is the same answer as we had before. So this is the logic we're going to use when we're asked to get the average value of any function. So what we're being asked to average value is basically, right, if we had a constant working through there rather than the curve or the function that we have, what would that constant be? Remember that that constant is, in this case, I'm talking about a horizontal line. So let's look at the little diagram I have here. We have a function which is f of x, which between a and b is going up and then going back down. But if we were to think of that as a constant shape, so the rectangle, what would the height of that rectangle be? So we could work that with the idea of the area. So imagine we find the area of the shape. So underneath the function, let me kind of shade it in so we see what we're talking about. So let's find this area here using integration. So that's the actual area. We then are going to divide the area by the base, so we can work out that distance from the base of the base, which is between A and B. So we do B take away A, which will give us the base. And then the area divided by the base should give us that constant height. So the height that it would be if it were a rectangle. So that's effectively what we do when we have average value. And this is our formula. We're dividing by b minus a, so we write that in terms of a fraction as 1 over b minus a, and we multiply that fraction by the area, which is just from the integration. So effectively, this is the integration, the area, divided by b minus a, and to do that division, we write it as a fraction. So this is a formula that you need to learn off by heart, but it is good to kind of understand where it comes from. So our formula is this here, 1 over b minus a, and then we do the definite integral to find the area between a and b of the function. Now, when we're asked average value, sometimes students are saying, but is average not add and divide? And when we're asked that, the idea of adding and dividing, chances are they're going to use the word mean, so M-E-A-N. So generally speaking, if you see the word average, you're probably being asked about integration, especially if it's average of a function, because a function is continuous. When we add and divide, that's for discrete pieces. So that's for individual pieces that can be added and divided. Here we're talking about a continuous function, so one that's not easily broken into discrete pieces because it's constantly changing, and that's why integration will give us a better answer for our average value. So here's an example. Find the average value of the function below. So we're going to basically use our formula. We have 1 over b minus a, which is 2 minus 0. We're going to integrate between 0 and 2. And we're going to integrate the actual function. And that's with respect to x. So I get a half of, when I integrate this, I add 1 to my power, divide by my power, and I add 1 to my power, and I'm going to integrate that between 2 and 0. That that half kind of just sits outside. I'm going to put a kind of big bracket here. My first substitution is 2, so I get 2 cubed over 3 plus 2, minus my second is going to be 0 cubed over 3 plus 0, and then we work that out as a half. This first bracket is 8 over 3 plus 2, and that gives me 14 over 3 minus 0, and then working that through, a half of 14 over 3, so that gives me 7 over 3. And again, this is not going to be square units. What this is effectively telling us is, if I were to draw this as a rectangle like this with the same area as the shaded piece, this height would be 7 over 3. That's what the average value is telling us. So let's take a look at an exam question. It's very hard to kind of just do an average value question because it tends to be very linked into the rest of the question. So this is question 8 part C of the 2021 paper. But you'll find this average value asked in quite a lot of questions. So anytime you see the word average, think, can I use my integration formula? So we're going to have 1 over b minus a. So they gave us our b and our a here. So it's 75 minus 0. We then set up our integration using those as our limits. We then have our function, which is 0.001x cubed minus 0.12x squared plus 3.6x plus 5 with respect to x. So this is 1 over 75. Let's actually integrate this. So you add 1 to your power. So that's x to the power of 4 divided by 4. Add 1 to your power, x to the power of 3 over 3. Add 1 to your power, 3.6x squared, divide by your power, plus 5x, and we're going to do that between 0 and 75. Let's just do a little bit of cleanup on this rather than having to deal with decimals and fractions. So I have 1 over 75. This is going to be 0.00025 x to the power of 4, or you can leave that as 1 over 4,000, minus 0.04x cubed plus 1.8x squared plus 5x, and then we can sub in 75 and 0. Now when I sub in 0, because I am subbing directly into x here, I'm going to get nothing. So I'm going to be a little bit cheeky there and not sub that in. So I have 0.00025 75 to the power of 4 minus 0.04 75 to the power of 3 plus 1.8 75 squared plus 5 times 75, and then effectively I would end up taking away a 0 there at the end, which is going to make pretty much, well, going to make absolutely no difference. So just if you want to do that, just be very, very mindful that subbing in a 0 does not always lead to a 0 answer, especially if we're doing trigonometric functions or if we're working with ease. So let's go to our calculator for this. So just have a bit more space to do that. 1 over 75, and when you work this through, get 1535.15625, and that works out as 20.46875 meters. It asks it to 2 decimal places, so 20.47 meters. So that's our average height. So watch out for that word average, and that's a way of bringing integration into kind of any type of function question, specifically in our section B's.